apresentação, seguido por 5 de perguntas, Leandro.
Tá ok, então, Opti. Muito obrigado aí pela apresentação. Bom dia a todos. Agora eu vou apresentar, então, meu trabalho. My name is Leandro, and I'm currently postdoc research at the University of Cabo de Santo Agostinho, Pernambuco, under the supervision of Professor Reza, and my work is focused on synthesis and the characterization of new functional materials based on copper complex and quantum dots incorporated in Mesoporous silica matrix. Let's put a point here. Okay. And through the manipulation of molecules, it's possible to build materials on the nanometric scale with different properties. The nanoscale will give us new properties when compared to the bulk materials. And the hybrid material is not different. The combination between organic and inorganic materials at the molecular level will give us a combination of properties of both materials at nanometric scale. For example, copper complex is a compound obtained by the combination of metallic copper ions and organic ligand to obtain the compound. And the copper complex has application in gas sensor, OLEDs, vapochromic and solvatochromic materials, catalysts, and among others. And recently is being requested for third generation of OLED due to the high internal efficiency and generation light close to the 100%. Here I will present you the tetranuclear copper complex, which has different emission at visible spectrum according to each coordination ligand. Each ligand 1 to 7 here, when combined with copper iodine complex, will form complex with different emission in the visible spectrum. Here, for example, the complex are under ultraviolet excitation, and it's possible to see different emission colors here. For example, the combination of ligand 7 is pyridine and copper iodine will form the tetranuclear copper complex. There are 4 copper atoms here in the center, forming the inorganic cluster around the organic pyridine molecule. Here, for example, is the emission spectrum for all these compounds. The number 3, for example, has emission around 700 nanometer, while number 6, compound number 6, has emission around 400 nanometer. And there, on the right side, we have the table with corresponding compounds with your number and maximum excitation and emission here. Copper complex presents thermochromic effect like we can see here. The emission at low energy here is very intense at room temperature, while the emission at high energy here is intense at low temperature. The low temperature induces some distortion and increase of the distance between the copper atoms like you can see here. And now I will talk about the process of obtaining Mesoporous silica matrix by the sol-gel process. The precursor of the synthesis reaction is tetraethylsilane, as we can see here. You can see the silicon bonded with 4 ethoxy group here that will give us the Mesoporous silica matrix by the reactions. And here, after acidifying the medium, will occur some hydrolysis of the hydrolysis reaction here, then the condensation and polycondensation with water release. After 1 week, the sample is heated 100 degrees to eliminate the water, and to obtain the Mesoporous silica matrix, surfactant is dropped here during the polycondensation reaction, and then extracted with organic solvent to release the pores. Here I will present you some methods to incorporation used in porous matrix to obtain optical materials. For example, here we have wet impregnation, covalent binding, ion exchange, and co-assembly. And it's possible, in this case, each process will give us different materials with different properties. And here I will explain a little bit about the porous formation. And after formation of the pores by the surfactants here, molecules, the matrix presents free pores here and can be filled with luminescent species, as you can see here. Wet impregnation and co-assembly method is more easy than binding covalent binding, because it's necessary to perform the functionalization of the silica surface with binders that will give reaction between the metal inside of the pores, like you see here, like you can see here. It's not easy to do. And here, in this work, I will present you new optical materials obtained by the wet impregnation method. And the material obtained from incorporation of copper complex and the quantum dots inside of mesoporous silica will give us materials with a new functionalities like gas sensor, solvatochromic, and rigidochromic effect. The definition of microporous and the mesoporous materials is related to their size. For example, microporous materials have a pore smaller than or equal to 2 nanometers, while mesoporous materials have a pore between 2 and 50 nanometers. For example, these samples, the pore size found was 10 nanometers or 11, according to the absorption isotherm here. And here in the left side, you can see the scan electron microscopy for the same sample. And this figure shows the emission spectrum as a function of oxygen concentration for 2 different copper complexes inside of mesoporous silica matrix. The emission intensity here decreases with increasing concentration of the oxygen. And the emission quotient is related to the activation of a triplet state by the oxygen. And here, for quantum dots incorporated in mesoporous silica, the same behavior was also observed here. The pore provides great dispersion of the quantum dots and great interaction with oxygen. And after quantum dots is excited with light with energy close to the band gap, occurs some energy transfer to the oxygen. And then after this, reactive oxygen species is formed. This reactive species absorbs on the quantum dot surface, creating a trap side that hides the electron hole reactive recombination. In other words, we have the equation of the emission of the materials. And here, the Estrin-Vollmer constant can be obtained by the ratio of emission intensity as a function of oxygen concentration according to this equation here. This equation or this constant gives us the degree of sensibility of the sample when exposed to the oxygen. Right? And high constant means high sensibility of the sample. Here you can see the emission spectrum for a copper complex inside of mesoporous silica with different concentration. Here we have 0.5 millimolar, and we will increase in this way until 5.0 millimolar increased concentration. The increasing in the concentration of the copper complex in the pores decreases the detection of sensibility, as we can see here, and the corresponding Estrin-Vollmer constant here. For this reason, it's necessary to study the good concentration for a sample according to your application. Here is the scheme of the apparatus used to measure the emission as a function of oxygen concentration. After mixing, the gases arrive at the excited sample where the signal is collected by the detector here. And here, it's possible to notice the reversibility and the reproducibility of the emission in the presence of oxygen and nitrogen after a few cycles here. And the right side, you can see the picture of the sample under emission after being exposed in the nitrogen and oxygen. And here you can see the Solvatochromic effect was also observed for complex incorporated in Mesoporous silica. And here, after being in contact with organic solvent, the sample changed the color after 3 minutes. And after 3 minutes, the sample returns to the original colors, as we can see here. And this effect is also seen in isolated complex. And when exposed to the acetonitrile solvent, the complex turns yellow. And after putting another solvent here, it's returned to the original orange color. By X-ray diffraction, it's possible to observe a distortion between binders caused by presence of solvent. As you can see here in the right, the solvent molecules has an interaction between the binders of the copper complex. And another effect observed after incorporation of a copper complex into Mesoporous silica matrix was the Rigidochromic effect. And this effect is caused by the rigidity of the environment where the complex is hosted. This rigidity of the matrix increases the energy level of the complex emitter state, shifting the emission to the blue. For example, we have here the copper complex isolated, has a red emission, and after incorporation into the Mesoporous silica, you have a green emission. For the conclusions, the incorporation of a copper complex and the quantum dots Mesoporous silica give us new materials with new functionalities, like oxygen sensing, rigidochromic and solvatochromic effect, and luminescence. And the next step is to build the up-conversion nanoparticles with the Mesoporous silica shell to incorporate the copper complex and the quantum dots to get multifunctional nanoparticles for thermometry, bioimaging, and photodynamic therapy too. This is our next step. So I would like to thank CNPq and FACEP for the financial support, and thank you all for their attention.